All right, guys, I want to talk about this topic called hotspot volcanoes. It's in relation to where our plate tectonics ideas, our earthquakes ideas, some of the things that we've been talking about with our dynamic planet. So that's kind of our last bit of our unit 4 here. Dynamic planet just means that our planet is changing all the time. And one of the big changes are the things that are happening here related to plate tectonics. So let's just describe what hotspots are, and let's go to our reference table and take a look at this page that we've been looking at with tectonic plates. Obviously, we talked about the borders, the boundaries of all these plates, how they're moving, how they're colliding and diverging, and all that stuff. But I never mentioned this little thing that's in the bottom right-hand corner called mantle hotspots. So you see these like little explosions, and they're all over the map here. Some of them should be familiar to you, like Hawaii and Yellowstone and maybe Iceland. These are areas in the world where there is active volcanism happening on a pretty regular basis. Okay. And the reason that's true is because of what's going down below the crust, below our feet. And what I want to do is I just want to show you, I'll just demonstrate this with a picture. So I'll come to my my piece of paper here. So just think about like the layers of the Earth. So here's the surface, there's the crust, okay? And down below the crust, I'll just draw this little thin layer. That'll represent the crust at the surface. And down below that is this layer called the asthenosphere, okay? So within the asthenosphere, A-S-T-H, astheno, okay? And this is the crust right here. Within this layer of the asthenosphere, remember we have all this motion, we have movement, we have convection happening due to differences in temperature within the asthenosphere, and that's what drives these plates, moves them across the surface. Okay, so in some places we actually have melted material, and we call that melted material, we call that a plume, P-L-U-M-E. Okay, a plume. And this melted material, this magma below the surface, is going to kind of move its way up because it's less dense, and then it's going to form a volcano at the surface right above that. So there's my volcano kind of erupting right there. All right, and this plume might have its origins from somewhere down deeper below, down here in the mantle, or all the way down to the outer core. And so you might have this rising material up to this plume where it's melted, and then you have a volcano that is going to form on the surface above that. Obviously, this is in no way to scale. Okay. Now, the interesting thing is, if we have melted material here called a hotspot, so this is the hotspot, this area. If we have melted material right there at this spot, we would expect that the volcano would just get bigger and bigger and bigger and grow and grow and grow and grow, because we have this melted material just right there, stationary. However, what we see is actually a chain of volcanoes that develop over a long period of time. So you can think about this because we have this top crust moving across the surface. So it moves maybe that way. So over time, I'll just draw that down here. Draw another, there's my crust, there's my plume, okay? And what's gonna happen is, if this moves this way, if this plate moves this direction to the right, well, I'm going to have a volcano here that forms, and then over time this volcano will move off to the right with the entire crust, and eventually it will be over here. Okay, so it's moved off to the hotspot. Well, what's going to happen over here? Well, we're just going to form another volcano, and it's going to move off to the right, and now this one, we'll call that number 1, this one is going to move over here. Okay, and now number 1 is going to be over here. Okay, so it's moved off to the right. And so we just get this chain of volcanoes extending away from the plume. So we can tell which way plates are moving just by looking at these volcanoes and the direction of their chain. So if you can think about like the islands of Hawaii, let's go back to my slideshow here. If if you look at the islands of Hawaii, here they are, you see multiple islands of Hawaii that were at one time all active volcanoes. This one, Maui, and Molokai, and Oahu, and Kauai, they were all at one time active volcanoes. But now they're no longer active because they've moved off of the hotspot. And we can figure out where the hotspot is located right here because this area of the big island of Hawaii is active. It is over top of the hotspot. It is over top of that mantle plume that I was referring to. Okay? And so if you take a look at this picture, which shows you ages of the volcanoes, ages of the rock, you can see it gets older and older and older the farther away you get from where it's now active in Kilauea. Okay? So we can kind of get an idea of the motion of the Pacific plate. We can tell which way it's moving because it's going to move in the direction where it gets older. So these older volcanoes over here were one time over top of the hotspot over here, but they've moved off. Okay? And this kind of shows the exact same thing. And so it's active right here. The plume is right underneath of the big island of Hawaii on the southeast side, but this entire plate has moved over top of it. Now, another way of demonstrating that, and I typically do this in the classroom. Let me show you something that I typically do in the classroom. I use a whiteboard marker to kind of demonstrate this. So imagine that the whiteboard marker is the plume, okay? And what I'm going to do is I'm going to put this plate, this piece of paper, let me just zoom out a little bit here, move my camera up a little bit so you can see a little bit better. Okay, and what I'm going to do is I'm going to take this plate, my piece of paper, it's going to represent the plate, and I'm going to put it over top of that active magma. Okay, and what's going to happen is it's going to sit over top of it, and it's going to eventually melt the crust, and it's going to form a volcano in that area. So you can kind of see it's bleeding through the paper. Now what I'm going to do is I'm going to move the paper down in your screen. So what you'll see is over time, okay, so you can start to see, oh, now it's melting over there, and there's an active volcano there. And now, the plate is moving down your screen, and you can almost see a chain developing on the screen. Okay, so now it's active right there. So if I look at the big picture, I can see, well, right here, the bottom picture, that dot right there was the original volcano, and now the volcano is right here. Okay, so we can kind of tell which way the plate moved, which way the paper moved, just by saying, okay, this is old, that was the original, this is new, and my paper moved down that way. So I know which way the plate moved just by looking at new to old. Okay, and that's the exact same thing with this picture here. We know which way the Pacific plate is moving because it's from new to old over here. Now, another interesting thing that's happening with this, obviously you have active volcano here building up the side of this island. So it's actually really, really tall. In fact, this island is technically the tallest mountain in the world if you were to eliminate the water. Mauna Kea is taller than Mount Everest is if you measured all the way to the bottom of the ocean. But as these islands get further and further away from the hotspot, they're not active anymore. They're not building up. They're not constructing the volcano. Other forces are at work destroying the volcanoes, those dormant volcanoes, I should say. And therefore, they kind of wear out and they get smaller and smaller until eventually they're down below the ocean. And we call these seamounts. And so if you look along this entire chain, this is the whole entire Hawaiian ridge, there are seamounts that extend away from the big island of Hawaii up towards the northwest. And some of them are still sticking up above the land, or above the water, I should say. But most of them are down below the water. They're called seamounts. They've been essentially worn out by the processes of weathering and erosion, which is something that we're going to talk about next after this topic. Okay. Now, this was a lab. This is a lab that we would typically do in the classroom. We're going to skip it this year. But we just look at the ages of the volcanoes and their distance away from where it's active, right here on the southeast side of the big island of Hawaii, Kilauea. And we would make a graph out of that would look like this. And you can see, obviously, there's a direct relationship here between the distance away from where it's active, 0 years old, okay, and Kilauea, And the age of the volcano, as it gets further away, it gets older. Okay, so there's just a nice direct relationship shown there, and we'd answer some questions related to that. Now, this is not only true of Hawaii, it's also true of all the other hot spots that are right underneath of moving plates. So and obviously you guys know about Yellowstone. Yellowstone is in northwest Wyoming. It's actively volcanic here, but there are old volcanoes, old evidence of volcanism that are out into Idaho and out into Oregon. And so the whole entire North American plate is moving, and we can tell which way it moves because here's where it's new, here's where it's old. So the plate was moving this direction, or it is continuing to move that direction toward the west. Okay, so that's another example of that. Now, another interesting idea comes about when you think about what if the plates weren't moving? And there's another volcano called Olympus Mons. It's the volcano on the planet Mars, and it's huge. It's massive. I can't even describe how big this is. The pictures really don't do it justice, but you can see, compared with Mount Everest is about 5.5 miles tall. Mauna Kea, if you measure it from the bottom of the ocean, is 6.3 miles tall. But Olympus Mons is 14 miles tall. It's ridiculously high. Really, really big volcano. And it's really, really large. It's like bigger than both of them combined, okay, as far as the area of the base. And that is because there is no active plate tectonics on Mars. In other words, the plates are not moving. There's no motion. It's not moving the volcano away from the hotspot. It just keeps building up and building up and building up and building up. And it just gets taller and taller and taller and taller. And so if we didn't have active plate tectonics on Earth, we'd have a really, really large volcano in the middle of the Pacific known as Hawaii. But we don't. We have just multiple islands as a result of it. So just another evidence for plate tectonics. Okay, so again, let me just review typical questions that you would probably see. Which way is the Pacific plate moving based upon, let's say, this picture? Well, we can tell by saying, okay, it's new here, it's old here, it's moving from new to old, so it's moving that direction to the northwest. And the other type of question that you might see is, where would the next island form after Hawaii moves off the hotspot? And that would be right over here to the southeast of the island. And you can actually see it's starting to form and starting to build up right here off the coast, off the southeast coast. That is called Loihi, and that's going to be the next island, technically, of the Hawaiian island chain. And so that's forming right here. It's actively volcanic right there as this moves over top of that hotspot. Okay, so hopefully that all makes sense. And if you have any questions about any of this, just let me know.